In the previous video, we looked at n way of extending the factorial. So we have s factorial is the limit as n approaches infinity of n to the s. The Pochhammer symbol is 0 sub n over s sub n, where the Pochhammer symbol is this polynomial. So something that you could try and do, you might notice is, well, first of all, we said that the Pochhammer symbol 0 sub n is this n factorial. So we could actually write this part as the limit as n approaches infinity, n to the s n factorial over s sub n. Now this numerator, it's never 0. Why is it never 0? Well, we're taking it like a whole number and raising it to some power. And we're saying when we raise a positive number to some power, it's never going to be 0. And the same way, if you take the factorial of a positive number, it's never going to be 0. But this could potentially be 0. In fact, it's 0 whenever it's a root of this polynomial. So that this polynomial has a root set -1. So it becomes 0 when x is -1, -2, all the way up to -n. So this this limit blows up when s is a negative number, which usually wouldn't be a problem because we don't take negative factorials. But in this case, we're trying to extend the factorial. And so what we could look at instead, this is the limit of s factorial. We could instead look at the 1 over s factorial. Actually, the order of these two don't matter. I just kind of switched them because I didn't want to look at like we're factoring all of them or something. So if we look at it like this, then we no longer have that problem that we had before. The denominator never goes to 0, but this could be 0. So we know that, for example, if we do 1 over -1 factorial, even though we can't really work out what -1 factorial is, just by plugging it into this part becomes 0, and when we take a limit, this just gives us 0. And so this in fact gives us a value for 1 over s factorial for every single s. So now next we're going to talk about this brilliant idea by Euler. So Euler saw this and he did the following. He said, well, what if we take 1 over s factorial? And his idea was, what if we could cancel this out? So to cancel it out, we would need a 1 over n minus s. So he thought, why don't we multiply it by negative s factorial like this? So because both these converge, this is equal to the limit as n approaches infinity, s to the n. Then we have minus s to the n from the minus bit. We have n factorial, n to the s, and n factorial, n to the minus s. And so these two cancel, and so we have limit n goes to infinity, s n over n factorial times n factorial. Okay, so it's a bit unclear what this is right now, but if we actually write this out using the actual polynomial definition for it, then it becomes slightly clearer. So this would be equal to s plus 1, s plus 2, and so on, up to s plus n. And then this part would give us minus s plus n, minus s plus 1, minus s plus 2, all the way up to minus s plus n. That kind of went off the page. And then we're dividing by, for each of these, we can divide by from 1 to n. Yeah, we can divide by 1 here, 2, all the way up to n, and over here as well, we divide by 1 here, 2, all the way up to n. And so we have 1 plus s over 1, 1 plus s over 2, all the way up to 1 plus s over n, then times 1 minus s over 1, 1 minus s over 2, and 1 minus s over n. And don't forget, we're taking the limit again, I keep forgetting. So we could actually write this limit in a different way. We could write it as limit n goes to infinity. And look, we're taking the product of 1 up to n, and then we can think of this as a -1 up to negative n, or the other way, negative n all the way up to -1. So we're taking the product. So we want k equals negative n. So that's from here. And we want it to go all the way up to n. But we don't want k to be 0 because then we have 1 plus s divided by 0. That's one term we miss out here, so k is not equal to 0. There's a nicer way of writing this, right? We could write it like 0 greater than absolute value of k less than or equal to n. And so then we have 1 plus s over k, like this. So there's one last step to it. So let's write what we just found on the other page. So we have 1 over s factorial. 1 over is the product of 0 greater than absolute value of k less than or equal to n of 1 plus s over k. So this is a pretty simple formula. But what do we do with this? Euler noticed this product here. I don't know exactly how Euler noticed it, but Euler is a genius and he noticed it. He noticed that this product here is equal to sine of pi s all over pi s. Now, we're not going to show this is true. And one way you could show this is true potentially is using something called Euler's theorem in complex analysis. It says that if the ratio of two functions is bounded, then it's constant. So you could prove it by taking the ratio of these two functions and showing that it's bounded. It's an analytic function and that it's bounded. And then you just need to work out its value for just one number. Alright, so how does this help you at all? If we plug in s equals a half into this equation, we get 1 over 1/2 factorial over negative 1/2 factorial is equal to sine of 1/2 is 1 and pi over 2, like this. And you could actually get this via something known as Wallace's product. So this is 2 over pi. And now, so if we want to work out 1/2 factorial, which would be nice, then, you know, negative 1/2 factorial would be 1/2 factorial like this. This is just the recurrence relation for the factorial, right? N factorial is n times n minus 1 factorial. So we can that means if we just multiply both sides by 2, we get that, and substituting this into here, we get that 1 over 2 factorial squared, right, because we get 2 of these, is equal to 2 over pi. And then we can multiply both sides by 2, and we flip it, so we get 1 over 2 factorial squared is pi over 4. And finally we get that if we square root both sides, because of the graph, you can kind of see that 1/2 factorial should be a positive number. We square root it and then we get factorial is square root pi over 2, right? So maybe like the bit that's sketchy is probably this. So actually the thing I recommend you to do is remember how in the video where we did the s factorial, we actually plotted it on Desmos. So what you could try and do is you could try and we'll try and plot this on Desmos. Yeah, you need to split it because Desmos won't let you type this in. Just split it into something that goes from k equals -1 all the way up to minus 1. So k equals -1 all the way up to -1. Then multiply it by something that goes from 1 all the way up to n. Send n to some large number, and then you can then plot this as well, and then you'll see that these two actually give you a function. And that kind of gives you the idea. So that's it for this video, right? So the main idea was that we have this, which is known as Euler's inflection formula. And so this is the end of this video. Thanks for watching.